Is it due right now? Okay. If you want to come find me during TA, I'll have more time. See if I can follow it.
That doesn't really settle. You have to explain that way.
All right, guys.
I think you already discussed
Like the setting, I never know there is something that
I see about
with the I can do that with the mid width.
but this is a really simple thing.
Yeah, I haven't yet.
Okay. So what we're going to do today is to wrap up the discussion. Finally, we are going to finish the discussion on functional dependency for the normal form. So I'm excited about it because we are able to move on to the next topic. And the next topic we're going to discuss will be about transactions. Some of you actually asked me about the concept of transaction and how you can use that in your application. To give you a heads up, what transaction is about is to enable concurrent execution against a database. So far, if you think about what the assumptions we have made in our discussion, when you execute queries and update to the database and performing normalization of the schema and so on and so forth, the implicit assumption we have made is that you are the only person accessing the database. There are no other person making changes to the database while you are making all these queries, refinement to your database. But in practice, we know that's obviously not the case. If you go to Amazon.com, millions of users may be accessing the website at the same time. Maybe not millions, but it's definitely possible hundreds of other users are looking at, browsing at the same item or same page from Amazon.com, connecting to the same database record in the backend with you together. And how do they ensure consistency and in that case is an interesting challenge. That's something we're going to talk about today. But before that, we do need to complete the discussion on normalization. And what I'm going to do today, we're almost there. What I'm going to do today is to just run through one or two examples that I skipped from last lecture about decomposition of BCNF and certain form, and have a little bit of concluding remarks regarding certain form. Then we're done. We're okay with respect to that. Any questions? And your homework 4 is due on Wednesday, and your project, let me remind you, is due on April 25th, which is still seems like far away, but so it always comes sooner than you realize, right? Like a train, right? When you realize it's too close, it's already like this big, you know. So start working on that earlier than sooner than later. That's my recommendation. Okay. If you have any question, and one of you brought up a really good point, which is you like to receive some feedback. We have completed the grading of your phase 1. We are making the final pass to make sure the scores are consistent and all that. And TAs will release your score later today on your phase 1. Then they will move on to grade your phase 2 of your project. A really good point brought by one of you was you would like to see the grading of your phase 2, not so much about the score you get, but also whether you implement certain functionality right or not, so that you can fix the mistakes you have made going into phase 3. I think that's a really valid point, and we will try the best we can to finish the grading of your phase 2 by the end of next week. Please bear with us because it is a heavy load of grading the TAs are doing. So and they are students themselves, right? They are taking classes and all that. So I don't want to push them too hard. So I will try to work with them to finish the grading of your phase 2 by the end of next week, which means you still have about 2 weeks left in reviewing your graded phase 2 while working on your phase 3. Does that make sense? I hope that helps. That's a big question.
We didn't use prepared statements in phase 2. Do we need to switch over?
No, you don't have to.
Okay.
Prepare step, no, you don't have to. Keep in mind, this is not a real world scenario where you have to worry about all these efficiency, security issues. The focus here in our product is really to give you an exercise to go through the entire workflow. So we focus pretty much primarily on whether you have demonstrated you can complete this functionality or not. So that's the primary focus of the product. Yes?
I was just wondering with phase 3 grading, are the tests that you're going to run against essentially our model, are those going to be like the same tests like we used in phase 2?
Yes.
So as long as we don't get anything as the model is right from phase 2, we should be good for phase 3.
Yeah.
We don't really need to perform a bunch of additional
Totally.
tests.
Dealing is completely right. In most scenarios, you expect a similar score or better, obviously. Either similar or better score for your phase 3 compared to your phase 2. Why? Because functionality-wise, and the test cases we're going to run will be the same for phase 2 and phase 3. You could be doing better because you have a little bit more time to work on phase 3, so that certain functions you didn't have time to fix or complete in your phase 2, now you have opportunity to do that. The only scenario where I see you may be doing slightly worse in phase 3 than phase 2 is that you are new to the web programming interface, and because of that, you are not able to complete the GUI required for certain functions. That will, of course, take a sting on your score, right? But other than that, I don't see anything that prevent you from doing at least the same or better in your phase 3 than your phase 2. Does that make sense? And the one thing that's really important for your phase 3 is to understand the concept of session, because you will need that to enforce logging in a web environment, and you will need the session in order to maintain state variables. For example, there's one function that requires you to, oh, welcome to the class. I was thinking to bring my daughter to class today because it's spring break for her as well. So, but luckily I found a last minute resolution for that. So welcome. Okay. Now, where I was. So there is one function I think is making order. The requirement is such that you want to enable users to add orders. Sorry, not order. Add places they have visited more than one in one particular session, meaning that you do not add this visit instance back to the database immediately after user has added. Rather, you allow the user to add one or multiple of this visit, then there's the final confirmation page for user to do that. Kind of like when you order things on Amazon.com, you have a, what's the concept? A shopping cart, right? Yeah, shopping cart, kind of like a shopping cart. And in order to support that, you need to use session, right? In phase 2, you implicitly supported that. The reason is, in a Java program, session is automatically maintained because it's in your program stack space, right? So session is implicitly maintained by the programming framework that you're using, which is Java in that case. But in a web environment, things are a little bit tricky than compared to programming language session, right? So you need to understand the concept session. In the tutorial I posted on the home page, there is a simple GSP tutorial, and one of the chapters is dedicated to this topic. It's actually quite straightforward. I will basically give you guys some time to explore this space yourself, and probably sometime next week or the week after, I will spend about a few minutes to go over this topic. But if you have questions, go ahead. Yeah.
Sorry.
No.
I guess I was just wondering then too, because it says we're not supposed to commit them into the visits into the database until we're done, but like in that state of, I guess like can you have like a map from like user to like a list of visits that you maintain in the server, or does the server like, does it go down after each query? I guess, can we maintain objects like that, or does it have to be maintained in the database?
Yeah, so good question. So I think, let me try to rephrase what Dylan is asking. So session is a web per object that maintained by your browser. Okay? Does that make sense? Which means session is whenever you go to a website, unless you have disabled session support in your browser for security reasons. But by default, most browsers come with the support for session. Okay? So you can think of a session as a state variable that's able to maintain certain information about the state of your visit to a particular website. Whether you have login, if you do have login, what's your username? What are the things you have clicked? What are things that you have added to your shopping cart and things like that? Those go into session. You can view session in high level like a key value table, like a hash table, key value table. Has a key and the value for that key. You can have multiple such key value pairs. For example, login name is Feifei. Order item 1, value is this. Order item 2, value is this. So on and so forth. Does that make sense? And now the second part of his question is about what if your browser has been shut down or the server crashed? Do I need to maintain session across these cases, meaning a failed state, either at the client side or server end? The answer is no. You don't have to worry about that. We assume that in practice, again, that's the difference between our product and the real-world scenario. In real-world scenario, if you are Amazon.com, obviously, you want to make sure even if my server crashed, I can restore all the session variables so that my customer will not experience the loss of their information. For example, this customer spent 2 hours trying to find all the deals and add to the shopping cart. Then you tell him or her, sorry, you have to do this all over again. Your customer is not going to be happy, right? So in real world scenario, yes, you have to worry about this. But in our case, you don't. You don't have to maintain your session variables in the case of client or server failures. Does that answer your question? Okay, fantastic.
What was the chapter you said that explained sessions?
Louder?
What was the chapter you said there was?
I forgot which chapter. It's chapter 8 or 9. In the GSP tutorial, there's a link online. So if you cannot find it, just send me an email. I will give you the direct link to it. Okay. All right. So that's all I want to say about homework and project. Homework 4. If you haven't started working on it, don't worry. I think homework 4 is rather straightforward. I mean, if you understand the concept we talk about, it takes you, I think, at most 2-3 hours to work on it. Honestly, if you know the concept really well, you should be able to finish it in an hour. So it should be quite straightforward. And I understand normalization and functional dependency are quite challenging for some of you because these require deep understanding in logic and discrete math and so on and so forth. But if you look at homework 4, that's the type of problem you will see in tests and in your final exam. So don't be so upset when you are not able to understand some of these concepts. If you think you can understand the concepts so well, because the test will be about basic understanding of this stuff. I'm not gonna, of course, if I want to go deep, I can give you really, really hard question on these problems, but I'm not going to do that. I will just test you fundamental understanding, basic understanding of this stuff, like you have seen in your homework 4. So if you feel comfortable doing homework 4, you should have no trouble in doing the task and doing the final exams. Okay? All right, let's move on to the lecture. So this is where we stopped last time. I'm going to continue from right here. So what we said last time is about 3NF. To give you a quick review of what is a 3NF. So 3NF has 3 conditions, right? for any functional dependency in the closure of F with respect to a schema. So your input is what? Your input is a set of functional dependencies and a schema R. This is a schema, right? And your output is if R is in third normal form or not, right? So that's the problem we're trying to solve here. And step one you want to check is from F you want to derive the closure of F. You want to find all the functional dependencies that actually hold with respect to your input schema. Okay? Then the requirement is then you for each X determining A in the closure of F. Because here, if you think about closure of F, you can think about this as a set of functional dependencies, right? Meaning I can view F as functional dependency 1, functional dependency 2, functional dependency 3, until, I don't know, n functional dependencies. That's my view, right? N functional dependencies. Does that make sense? And this F, obviously, there's an implicit condition is that this set of functional dependencies is always a subset of the closure of F. And then this is for each of that, meaning that you go over, in other words, what you're doing here is for I equal to 1 all the way to n, you check this condition. And this is, let's say, Fi. Functional dependency, the I's functional dependency is written as X determines A. Does that make sense? You are going over each of the functional dependency here and you check these conditions one by one. Yes or no?
Yes.
Okay? And what you do is you check these conditions. What are the conditions? 3 conditions. The first 2 conditions are identical to the requirement of BCNF. In other words, you're checking whether this is a trivial functional dependency, if the right-hand side is a subset of left-hand side, or if that's not the case. If that's the case, you can stop already. This functional dependency is fine. With respect to both BCNF and third normal form requirement, you should move on to the next functional dependency, which means move on to Fi plus 1, Fi plus 2, and so on and so forth. If the first condition is not met, then you move on to checking the second condition, which is if X, your left-hand side, is X a key of your schema, a key of your schema. This can be a primary key or candidate key, but must be a, I took back what I said. It's a super key of your schema. If X is a super key of your schema. If it is, then this is fine. This doesn't violate either BCNF or 3NF requirements. Meaning if this condition is satisfied, you should move on to check the next condition. Next functional dependency Fi plus 1. Okay? If both the first 2 conditions are not met, meaning it's not a trivial functional dependency and the left-hand side is not a super key, then this tells you immediately, without looking at the other functional dependencies, regardless whether the other functional dependency satisfies this requirement or not, you know this schema is not in BCNF. Because BCNF also any normal form, to violate any normal form, you only need to find one such functional dependency. To satisfy a particular normal form, you need to make sure all functional dependencies are okay with respect to that normal form. But to violate the requirement, you only need to find one such functional dependency. Does that make sense? So as soon as you find one such functional dependency that doesn't satisfy the first 2 conditions, you already know this schema is not in BCNF. But it could be the case that this schema satisfies the third normal form requirement, because we relax the requirement on BCNF by adding another condition, and the condition is off, right? So if you think about it, if you have a predicate that says condition 1 or condition 2 or condition 3 versus the same first two conditions, condition 1 or condition 2, a claim you can make is if this is true, if this is true, you can imply that this is always true. But if this is true, it does not necessarily mean the second predicate is true. Does that make sense? So in other words, this is a relaxation of the second. If this is predicate 1, this is predicate 2. If they are being all together. If the second predicate is true, you know first predicate is always true. But the other way is not necessarily the case. So using this argument, you can show third normal form is really a relaxation of B, C, and F, because the first two conditions are the same and they are being all together. Okay?
Do you have time to do an example with attributes?
To do example for this? Well, I can give you a proof for this, right? If this is true, that means either condition 1 or condition 2 is true. Otherwise, this must be false. Right? But if any one of them is true, predicate 1 automatically is true, because you have 3 conditions, you require one of them to be true. So if either condition 1 or condition 2 is true, then this whole thing is true. I know. Because they are being all together. Does that make sense? Now, so that's basically third normal form. And you may wonder why we study third normal form. As we said last lecture, it is proved. I'm not going to go over this proof, but it's known that dependency preserving and lossless drawn decomposition into third normal form is always possible for any schema and input function dependencies. And the same statement is not true for B, C, and F. There are cases where you cannot have dependency preserving and lossless drawn decomposition into B, C, and F. Okay. So to give you an example here, so you can ignore the slides, and because I'm going to go over this example here on the whiteboard. Okay? So you can just follow me on the whiteboard. I went over this example last lecture, but it's kind of rushed, so I'm going to go over this once more. So I'm going to use our old friend, the reserve table, right? Which is, you remind you sailor ID, code ID, and date. Which sailor reserve which boat on which date. And the primary key of that table is all 3 attributes, meaning the same sailor may reserve the same boat on different date. If you have this as your primary key, that means the same sailor can only reserve the same boat once in the history of his or her reservations on this in this sailor club. But obviously, in most cases, that's not the case. You can definitely, in most real-world scenarios, you can always reserve the same thing multiple times on different occasions. So we make the whole thing as a key. Okay, so that's the schema of the reserve table. Now, we make it a little bit more real, close to a real-world scenario, because oftentimes when you reserve a boat, you need to supply some form of payment, most likely in a credit card, in the form of credit card. So the sailors club might want to keep track of your credit card information that you want to use to pay for this reservation. So I call that credit card number. So that's your credit card number used for it to pay for this. Does that make sense? Now, if I tell you, in my sailors club, I require you to use the same credit card to pay for your bills, to pay for your reservation. So for the first time you register in my club, I ask you to present a credit card, and you're going to use this credit card for all your subsequent reservations. If I tell you that's in my spec, that implies a functional dependency, which is, so I'm going to represent this table using S, B, D, C, the first letter of each attribute. Okay? So that's my R. Obviously, I know by the fact that this is the primary key, I know there's a function dependency which is this. Does that make sense? So my functional dependency set initially is just this. Okay? But now, I tell you, as the owner of the club, I tell you, everyone in my club, when they first register as a member of my club, I ask for a credit card information from them. And they're going to use this credit card to pay for all their reservations. If that's what you've been told, you imply you can derive a functional dependency, which is for the same sailor, you're going to have the same credit card. Right? Yes, the same sailor may carry multiple credit cards, but based on the spec I just told you, they have to use the same credit card for the reservation in this sailor's club. Does that make sense? So I have this functional dependency. Now this actually demonstrates to you the usefulness of the concept of functional dependency. Otherwise, you have to use this lengthy description in your spec. Oh, when sailor register, they show me a credit card, I'm going to use the credit card to make all the reservations. I don't know how many words of that is. That translates to only 2 characters and an hour. And that's all you need to do. Okay? To concisely capture that constraint. Okay? So that's one demonstration of how useful functional dependency is in practice. Okay? Now, that being said, I want to ask you, is R in B, C, and F? And is R in third normal? Those are the 2 questions I want to ask you. And the answer is no for both of them. The answer is no for both of them. Why is that? Because if you check the first functional dependency, it satisfies the BCNF requirement because it's the left-hand side is a key. Right? Why? Because if you check the closure of attribute closure of this guy, it's everything. So that shows you that must be a key. At least it must be a super key. Okay? At least it must be a super key. If it satisfies the BCNF requirement, automatically it will satisfy third normal form requirement. By the argument I just gave you earlier today. Right? So this is fine. But what about this one? Is it a trivial? Yeah.
So I was just wondering, so in this example,
Yes.
so sailors could you could have 2 sailors that share the same credit card, maybe they're like a husband and wife or something,
Yes.
right?
Yes.
Okay.
That's an excellent question. Delian's question is, knowing that I have this function dependency, which is sailor determined credit card, it means for the same sailor, you always expect to see the same credit card number in this database. However, what about different sailors? Can they have the same credit card, meaning brothers, sisters, or husband and wife? Can they present the same credit card when both of them are my sailors, right? Can they use the same credit card? Can someone tell me the answer?
I think yes.
You think yes?
Yeah,
Explain to me why.
because this says that sailor gives back the credit card. So with 2 sailors having 1 credit card, that is still whole.
Yes. So that's his argument. Let me materialize the argument using a concrete example. I may have sailor ID 1. Let's say sailor ID. I'm going to use name to be more. You can think about name as ID. Feifei. I have a credit card number. So my association is. No, give you my real credit card number. Live on YouTube. Okay. So if I make multiple reservations, you will see that I always use this number. Let's say my friend. Okay. Let's say I don't know, 52. It's my brother or whatever. For some reason, he doesn't have a credit card. Okay. Okay, so he said, Feifei, can I borrow your credit card? Being a really nice person, of course, I would say yes. Okay? Yes. Of course, I will check, how much it cost. Like $10. Okay, go ahead. So that's the situation. Okay. Does this violate this requirement? Obviously no, right? All it says, if you see another Feifei, what's the value here? It must be, cannot be anything else. If you see another FF2, what's the value here? Cannot be anything else but this. But if you see a value 1, 2, 3, 4, 5, 6, 7, 8, what's the value here? It can be anything. So that's the excellent answer. Okay. Now, this is not in BCM because this is not a trivial function dependency, and the left-hand side is not a key. It's not a super key. Why? Because if you look at the attribute closure of S, you start with S, then you can add the right-hand side of this function dependency to it, so you get SC, but that's about it. From this and this set of function dependency, you cannot derive any more function dependencies. So the attribute closure of S stops right here, stop expanding right here. So this implies if you're not a key, you cannot be a super key, right? If you cannot be a super key, you cannot be a key. So S is not a key, and it's not a key and super key. It's not either one of them. So a wireless BCNF and third normal form requirement. Now, the third condition in third normal form says, if both of them are not okay, meaning it's not a trivial function dependency, it's not a key function dependency, but, however, I can relax the condition by checking if the right-hand side is part of your key, if you're part of your key, The intuition, the intuition of having this relaxation is as follows. We all know key will determine everything else. If some other attribute determine part of your key, yes, it's going to introduce redundancy, but this is okay in some sense because there is an association between key and this value anyway. Now you are introducing a backward chain between this attribute and some part of your key. Yes, we're going to have redundancy, but this is better than this something determine something totally unrelated with this attribute itself. Does that make sense? Because the key and this attribute, this set of attributes has some sort of relationship to begin with. They already have this dependency, which is key determine this attribute or this set of attributes. Then having this attribute or this set of attributes determine part of your key, yes, it's going to introduce additional redundancy, but you guys have some dependency to start with. So that's kind of like the minimum redundancy I can hope for. So I allow that. So that's the intuition behind this definition. Okay? Now, let's check if that's the case. Is the right-hand side, first of all, by now we know this is not in BCNF. It's not a trivial function dependency, it's not a key function dependency. So it's definitely not in BCNF. But it is in third normal form. Well, the first two conditions are not met, otherwise it should be in BCNF automatically. We don't even bother checking third normal form in that case. Now we check is the right-hand side we check this. Is C part of a key? C part of a key? The answer is no in this case, because the only key you have is, in this example, the only key you have is ICBD. So this is not in BCNF, and this is not in third normal form. You follow? Now let me ask you a follow-up question, which is not, I don't believe I have that in the slides, which is, can I decompose this into a set of BCNF schemas using the decomposition algorithm we talked about earlier? Do you still remember the decomposition algorithm we talked about earlier? Which is, if you have x determine y, you decompose R into, of course, an implicit requirement is x intersect y is empty set, but you can always get that by making right-hand side a single attribute to begin with for any functional dependency. We talked about that, right? Does that make sense? AB determines CD is equivalent to AB determines C and AB determines D. So you can always make the right-hand side a single attribute so that x intersect y is an empty set. Why? Because we don't care about trivial function dependencies. In other words, if I have AB determine BCD, then this breakup becomes AB determine C, AB determine D, and AB determine D. But then I eventually remove this person. The last function dependency because it's a trivial function dependency. I don't care. So you can always make right-hand side a single attribute and x intersect y, meaning left-hand side intersect right-hand side is an empty set. All of you follow me on that? Now, my decomposition algorithm is, if you have this, and, of course, and if this function dependency is okay with respect to B, C, and F requirement, you don't do anything about it. You don't decompose your schema for something that's okay. You decompose your schema only if you find a function dependency that's not okay with respect to your B, C, and F requirement. You follow me? You decompose into, can someone tell me what do you decompose this into? Yes?
R1 and R2.
Yes? Fantastic. Oh, is that enough? It's like reminds me when we have a when I was a primary school student in China, when there was one geometry class, no, geography class, my teacher asked, what's outside China, right? He was trying to ask what are the countries outside China, like Russia and things like that. And one of my friends raised his hand and said, oh, that's easy. What's outside China, right? It's China and outside China. I mean, it's funny, but it's valid response. But do you have any follow-up to say about R1 and R2?
So I think R1 would be FBE.
Oh, I see what you mean. I'm not asking for this particular example, but in this generic setup, what is your R1 and R2?
It's the new relation.
Huh?
It's the new schemas.
Is that what?
The new schemas for the relation. Sorry.
Show me the attributes in R1 and R2. How about that? What are the attributes in R1 and R2?
The different attributes that you want to say.
Yes? What are those different attributes?
Yes.
Make a guess. You have x determine y, where there is B, C, and F requirement, and x intersect y is empty set. What do you decompose R into? Yes, R1 and R2, but what are inside R1 and R2?
Is it R1, R minus Y, R1 is Y, R minus Y, and R2 is going to be X and Y?
Yes. Okay. And you decompose this guaranteed to be lossless Jones decomposition. Why? Because we proved this, R1 intersect R2 is, by this condition, this means there must be X, and this determines, does this determine R1, does this determine R2? Whether this determines R1, I don't know. Because R1 is R minus 1, but I know for sure this determines R2, which is XY, because you have X determine Y. And by then, an earlier result we said, if the intersection determines one of them, this decomposition is guaranteed to be a lossless Jones decomposition. Yes or no? Okay? If you don't know what I'm talking about, that means you need to do a little bit of review. Okay? These are basic stuff we have just gone over in the past 2 weeks. So apply that. Now let's apply that to this particular example. How do I so it's not in B, C, and F, so I'm going to decompose this into B, C, and F. So how do I do that? I check. Is this okay? The answer is yes. The first function dependency is okay, so you don't have to do anything about it. We move on to the second function dependency. Is this okay? Answer is no, it's not okay. This violates BC and F requirement. And left-hand side, and S intersect C is empty set. So I'm going to decompose this. So now I'm going to ask one of you to do this, right? It should be quite straightforward, right? Just apply this. Okay, I'm going to call, what's your name? Yes. What's your name?
Steven.
No, I'm asking, yes, yes.
Blake.
Blake, okay.
Yeah.
Can you go ahead, Blake?
So what was the question?
Decompose this schema SBDC into two smaller schemas that are in BC and F. And I show you the first step. We check function dependency one by one. The first one, you don't have to do anything because it doesn't violate the BC and F requirements. What about the second? The second one does violate the BC and F requirements, so we have to decompose the schema with respect to that. Now, my question is, how are you going to decompose this? Based on the machinery I just showed you, right? You're going to use that particular construction to do this. How do you do it? Like,
I don't know.
okay, fine. That's a valid answer. Fine. Let's move on.
I think that you would take C from R1, which is from R, and then construct another R with S and C.
So your R2 is S and C. What's your R1?
Is SBD. That's it.
Okay. Why? It's a straightforward application of this. This is your R. This is your X. This is your Y. So R1 is R minus what?
C.
R minus Y, right? Which is R minus, which is SBDC minus C in this case. So it's SBD. R2 is what? X and Y, so it's S and C. And why this is defined? Because if you intercept them, what do you get? If you R1 intercept R2, what do you get? Equal to S, and S determines XR2, which is, and by the earlier theorem, I told you this guaranteed to be a lossless John decomposition. So you got SBD and SC. Another follow-up question I'm gonna, yes, question over there, all the way in the back.
Would it also be okay for R2 if it was BDC instead of SC, so that the BD is the same?
So you're gonna do R1 stay the same,
Yeah.
R2 is BDC, is that what you're saying?
Yeah.
Okay, you tell me whether this is okay or not. How do you check it?
Well, at first I think it's okay.
You guess it's okay? When you make an important decision in your life, you cannot say, I guess it's okay. Right? So you have to be, like if you buy a house, like $10, yeah, fine, I guess it's okay. But you buy a house $1 million, you don't say, oh, I guess it's okay. Right? You have to be sure, right? How do you be sure? Let me ask somebody else. I don't want to keep asking you. Yeah.
So my initial thought is it's not okay because nowhere in that split are you preserving the S implies C.
You reserve what, louder?
You're not ever implying that S, you're not ever stating that S implies C because you no longer have any sort of...
Okay. You brought up another aspect of this decomposition, which is whether this is a dependency preserving decomposition. Let's not come to that point. That's a valid point, but I'm not coming to that as yet. Can you tell me whether this is okay with respect to lossless John decomposition? Whether this is lossless John decomposition?
Let's say no.
No.
The
Okay.
intersection is BD and BD is not.
Okay. If you do the intersection of them, what's the intersection? It's BD. And BD doesn't determine SBD, BD doesn't determine BDC, so BD doesn't determine either R1 or R2. By the earlier discussion, that's a necessary and sufficient condition. This must be true in order for this to be a lossy John decomposition, and it is not true. So this is a lossy decomposition, so it's not okay. Anyway.
So this decomposition only allows us to decompose into lossless.
John,
Does
lossless
not
John.
guarantee dependency.
Excellent. It doesn't necessarily guarantee dependency preserving decomposition because lossless John and dependency preserving decomposition into B, C, and F is not always possible. So how do you check that? That's the next question before I was interrupted by that question, which was an excellent question, by the way. I was trying to get into, which is whether this, let me finish this and I will answer the question. Whether this is, so we know this is a lossless John decomposition. Now my next question is this a dependency preserving decomposition? Brandon.
So you have to check whether the functional dependencies of R1 and R2, the union of them is equal to the closure of F.
Okay, how do you check it? So let's try it out. So we are checking whether this is a dependency preserving decomposition or not. So your R is SBDC, and your R1 is SBD. Your R2 is F and C, right? So that's what we said so far. To check whether it's a dependency, we know this is loss. This is okay. We check it, right? The intersection them is S and S determine one of them. So it is guaranteed to be a lossless John decomposition. Is this a DPD, dependency preserving decomposition? How do I check it? Like Brandon said, you check the functional dependencies on R1 and R2 respectively, which is F1 and F2. So you need to know how to compute F1 and F2. We talked about this before. I'm just running this through as an example for you. Okay? How do you compute F1? Well, remember, the way to compute that is you compute the closure of the original functional dependencies, and then you project all functional dependencies whose left-hand side union right-hand side belong to a particular schema. If that's the case, that functional dependency goes to the functional dependency set for that schema. So for R1, it's SBD. Does that make sense? My F, in this case, is SBD determines C and S determines C. Does that make sense? Yes or no?
Yeah.
And you cannot derive any additional functional dependency from this. So your F closure is the same as your F. There's no more functional dependency you can derive based on this. Using this projection idea, what is the functional dependency hold with respect to R1? Can someone tell me what's in F1? The left-hand side and the right-hand side union together must be covered by that schema. Steven?
I think so. For SVD, the functional dependencies, the non-trivial ones, is going to be the empty set because all of them are key.
Yeah. The only thing you can derive is SVD determines SVD, but it's a trivial functional dependency we typically ignore. So F1 is simply an empty set. Excellent. Since you answered my question, I'm going to ask you to do me one more favor. What's F2?
Well, I think that's still, you've got S determine, or S implies C.
Anything else?
I think that's it, because you don't know that C implies S.
Excellent. Why is S determines C? Because, again, look at this definition. The union of left-hand side and right-hand side must be covered by that schema. So the union of left-hand side and right-hand side of this is SC and covered by that schema, so that function dependency is projected onto that schema. Is this going to be projected here? The answer is no, because the union of them is SBDC. It's not covered by the schema itself, so it's not projected over into that function dependency. Okay? Now, yes?
Do you mind rewriting that? I can't see it.
Rewrite what?
Rewriting what we have in topic for
Ah, it's this. It's basically I copied the set of function dimensions over. So maybe I should use a different color. Green, you cannot see green color. Oh, it's a shadow. Okay, got it. I will make sure I'm outside the shadow area. Now, the next question I'm going to follow up to this is, I'm going to move on to here, which is, okay, now I'm going to ask this question. Is this a dependency preserving decomposition? But I didn't show you what's F1 and F2 now, right? Now, follow up on his comment. Is this a dependency preserving decomposition?
No.
Huh? No. Brandon, you answered my question before, so I'm going to ask something else. You are next to Chaofeng. Yeah, what's your name?
Derek?
Derek?
Yeah.
I think I asked you a question.
Yeah, so it's not because
it is not. Okay,
yeah,
why? Explain to
the
me why.
functional dependencies we have in the original one are SVD to C and S to C, and all we have is S to C. And we have F2.
Okay, so I think what Derek is saying is the following. To formalize this argument is that the union of these two, and you check the closure of this, it's not going to give you the closure of the original function dimensions. Why? Because the closure of the original function dimension is essentially the same as the original set of function dimensions, which has two function dimensions. SBD determines C, and do you follow me? And what's the union's closure? Well, one is an empty set, the other is S determines C, so the only thing you have is, and the closure of this obviously is just going to be the same as itself. Nothing. Of course, we always ignore trivial function dimensions such as we ignore this, right? Because this is going to be true for both sets anyway. So you ignore them.
Can't you use it is non-trivial functional dependency, but I think you could still use it because SVD implies SVD, so you can split that up and you can say SVD implies S.
Yes.
Therefore, you can say SVD implies C. Correct? So I think it would be dependency preserving.
Oh, no. But on the left-hand side, you do not have this. The right-hand, this is fine. The problem is with this side. You cannot derive SVD determines C here. How do you derive that?
Well, if you said
I said trivial function dimensions are going to be present on both ends. Meaning, if you have S determines S, C determines C, you guarantee to have S determines S and C determines C on both ends. So there's no point of checking trivial function dimensions in this process.
But what I'm saying is that you still, in F1, you still
In
have
F1.
that trivial functional dependency.
Hold on, slowly. In F1 is an empty set. Remember?
F1, well,
F1 is an empty set.
we just treated it like that, but officially it still has that trivial functional
Oh, yeah,
dependency,
sure. You
right?
still have SVD determine SVD. Yes, no
We
problem.
still have that in there,
Okay.
but we just usually don't care about it. But in this case, it seems like it could matter because if you're taking
Oh, you're
F1
right.
union
You're right.
F2,
In this case, you're right.
and then
Okay.
taking the, yeah.
Okay, I took back what I said. Dylan has made a correction. This is important. I apologize for it. Actually, you don't have to look at the trivial function. Okay, you don't need this at all. What happens is, if you have S determines C, you can derive using augmentation. SVD determines C. That make sense? Why? Because we have the rule of augmentation. Do you remember? If A determines B, then you can always derive AX determines BX for any X. Right? You can add attributes to both ends, both right hand side and left hand side. You follow me? That's the rule of augmentation. You follow me? Yes or no? This is one of the basic rules, right?
No, I don't see where the BD, where the BD.
Okay, where the BD comes from.
No, on the right side, where is it? You added
Okay,
it above.
I'm gonna show you that, right? So that means that you're gonna do this is trivial, right? You're gonna have SBDC, right? And then using this, you can break up the right hand side into multiple attributes. Now do you see it? And these are trivial functions that you can ignore. You get this back. So dealing point is right, but you don't really have to using trivial functions to get it. Does that make sense? That my earlier statement is still right in the sense that you never need to worry about trivial functions. But what I overlooked is that you can actually from this derive this. So this actually, this actually are the same. These are the same. So this is actually a really good example to demonstrate to you that checking dependency preserving is not, you have to be a little bit careful in checking this. Okay, intuitively speaking, if S already determines C, adding more attributes to the left-hand side, as long as you keep S, is still going to be determining C, right? So if I myself can open this door, I ask for 2 or 3 additional helpers, as long as I'm still here with the key, I can obviously can still open this door. That's kind of the intuition here. Naturally, not your question.
Could you explain how F1 was made an empty set? I mean, I think I lost there.
Okay, because you use this rule, right? The closure of F is having only these 2 function dependencies, SPD dependency and SP dependency, right? None of them, if you look at the union of the right-hand side and left-hand side, none of them is contained or covered by the schema of R1. So the first one, the union of right-hand side and left-hand side is SBDC. It's not covered by SBD. The union of the right-hand side and left-hand side, the second one is SC. It's not covered by SBD. So none of them is going to be projected onto R1. So F1 is empty.
So what do you mean covered by?
Covered by meaning all the attributes are included in the schema of R1. Okay? All the attributes from left-hand side and right-hand side are covered or included by that schema. Okay? Yeah, question.
If you can see that projecting F1 and F2, projecting just from F, not the closure of F, just from F, is enough for their union to get F back? Is
no.
it necessary to do the closure?
No. There are cases where you need to check closure to get back the closure.
Right, so I'm wondering if you can see that in
If you can see it, yes, then it's not necessary. Yes. Yes.
Okay.
Meaning without using the closure, doing the projection already can get back to F or F closure, then obviously there's no need to using closure to do the projection in the first place. If you can see that. Okay, so this is a really good example. Now we have a decomposition that's both lossless join and dependency preserving into BC and F. So I'm going to skip the earlier example I skipped here, but I think it's similar, right? So I can just give you another example where you can decompose this into BC and F, lossless join, and dependency preserving. But there are cases where this is not possible. If I have time, I will go back to that example. Now, what about now? Finally, we finish this example, right? What about if I add another constraint, which is I'm not going to allow. Go back to the earlier observation made by one of you. I forgot who made a comment. Can 2 persons, I think billion, right? Can 2 persons have the same credit card amount? In our current design, the answer is yes. But what happens if I want to prevent that from happening? I said, every person must use the same credit card to make his or her reservation, and no 2 persons can use the same credit card in my club to make a reservation. Yep?
So wouldn't that imply C become a trivial dependency in that case?
No, trivial function dependency always refer to the case where right-hand side is a subset of left-hand side. That's the definition of trivial function dependency. Okay? So if every person must use different credit card to make a reservation, what does it tell you? What is the function dependency?
Do we need to add another functional dependency?
Yes, you do need to add another function dependency, which is
C implies S.
C implies S. Once you know the credit card, you know which person it belongs to, because no two person can have the same credit card. You follow me? Now let's go back to the same exercise again. Is this a BCNF schema? So I'm gonna keep going through that row. Next to Derek, what's your name? Michael. Go ahead. Is this in BCNF? Yes or no? Simple answer. No? Okay, why? Let me lead you through this, right? Is the first one okay with regard to BCNF requirement? Yes, why? Louder?
It's an enclosure.
It's no. It's because the left hand side is a key. Okay, fantastic. Move on to the second. Is the second function dependency okay with regard to BCNF requirement? Yes or no?
Well, S is in the key, but
Louder.
S is in the key.
S in the key. S is in the key, but S is not a key. So and it is not a trivial function dependency, so that fails already, right? Because you only have two conditions you can check for BCNF. So this is not okay with regard to BCNF. You follow me? So the same drill, right? So now I can ask you the question whether you can decompose this into a set of BCNF schemas, loss withdrawal and dependency preserving decomposition. I leave this as an exercise you do on your own. And check this like this. The only trick is there's one more dependency. You want to check whether that dependency can be preserved or not. Actually, you can immediately see actually it is preserved, right? Because as C preserved both S different C and C different S. So I can immediately tell you this is possible to be decomposed into loss withdrawal and dependency preserving BCNF schemas. Okay? But is the decomposition really necessary if I'm asking whether this is in third normal form or not? Is this in third normal form? There are two things, right? One is this, one is this. So comparing these two, right? I can ask the same question, is this in BCNF or not? I'm going to ask two of you, one answer if my function dependency is like this, the other person will reply to me whether my function dependency is like this. Andrew, if your function dependency is like this, is the input schema in in third normal form or not? No. No, tell me why.
If C isn't part of any candidate key.
Okay. This satisfies BCNF requirement, so obviously it satisfies third normal form requirement. Checking on the second one, it's not trivial function dependency, left hand side is not a key. So you only have the last condition to check for, which is whether right hand side is part of a key. But C obviously is not part of a key. The only key is SVD. So this has violated the third normal form requirement. So it is not in third normal form. So Andrew has answered that. Now moving on to this setup. If my function dependency changed to this, is this in third normal form, correct?
Yes.
Yes, tell me why.
Because on the C determines S, S is part of the key, so it's in third normal form.
Yes, this is fine.
Yeah.
Because the right hand side is part of a key. Because S is part of it. But what about this? C seemingly seems that C is not part of a key. Why this doesn't violate third normal form requirement?
I don't know.
You want to give a second thought to your answer? Or you want to stick with your answer?
I'm sticking with it.
You can stick with it, but you have to give me a reason why.
Yeah, I don't know.
Okay, all right.
Because C is a key for X person, so as C.
C is a key,
so
but
the
C is not a key.
Well, C, the closure of C would be CS, right? So
Okay, let's check the closure of C, and S. That's about it. It's not a key. C does not determine B and D. Remember, the right-hand side doesn't have to be a key. The right-hand side only needs to be part of your key, part of your key. 乔峰 You don't think this is the external form. So you think Greg made a wrong decision by sticking with his claim. Ross?
I don't think it's internal form.
You don't think it's internal form. Natalie said no. Okay. Who is sided with Greg? Who think this is actually in third normal form? Michael, right? Okay. Michael, help me out, please.
So, I think it is because, so we have one super key, right?
We have one super key, which is?
SB&D, right? So that's
SBD, yes, SBD, not only the super key, but actually the key as well.
Right.
Okay.
But because we've now said that C determines S, can't we actually say that C, B, and D is a candidate key?
Excellent. C and B and D determine SBD by augmentation. As SBD determines everything, SBD the key. If CBD determines a key, CBD must be a key. And CBD must be at least a super key. But third normal form, checking third normal form is tricky, right? The right-hand side must be part of a key. It's not part of a super key, because anything is part of a super key, because the whole schema is a super key. So to ensure is CBD a key? First of all, by this fact, you know CBD at least is a super key because it determines the key which determines everything else. So CBD determines everything, determines the schema. So CBD at least is a super key. To check whether this is the key, all you need to check is any subset of it. Can they be a super key? It's C, B, D. None of this is able to determine everything else. And then you check the combination of CB, BD, and CD. None of them is able to determine everything else. So this gives you the conclusion that CBD is a key. By that, you remove this question mark because the right-hand side is part of the key. So this is in third normal form. So checking BCNF and third normal form is really, not really tricky, but it's definitely trickier than you would expect. So this is kind of like magic, right? Person determining credit card, and that's not okay with respect to third normal form. And always not okay with BCNF. Now, person determining credit card and credit card determining person, as long as at that second condition, suddenly everything is okay. Why? If you think about it, it make a lot of sense, right? Per Dillon's earlier argument, if we only have person determining credit card, what do you have? You have that redundancy, which is multiple person may have the same credit card information, but now person determining credit card determining person, you still have redundancy because for every reservation this person make, you are still duplicating his or her credit card association values. If this person has made 1 million reservations, you are duplicating the credit card value for this person 1 million times, meaning you still have redundancy in your design. But at least it's better than having more dependency than just this, which is multiple person can also share the same credit card values. Do you follow me? So third normal form at least get rid of that. Yeah, that's it.
Can you just think of like, since we have SBD as a key, just saying since C implies S, just substituting S in for the C?
No? What are you saying? SBD is a key and
Yeah, and we know that C implies S, so can we do a
SBD
substitution?
determine SBDC. Okay, what do you want to do after this?
So, no, what I'm saying is, since S implies C, C implies S, can we just substitute in the key SBD and just say CBD? Because we know that S is...
So you're going to substitute, what you're trying to argue is this implies what? Implies CBD determines... You mean can I, using this, substitute S with
Substitute
C?
C.
Intuitively, yes. Intuitively, I see what you're saying. Because S determines C, in some sense,
C
it has S. Oh, C, okay, this C determines S,
Yes.
meaning intuitively, if you view this as a chain effect, right? C determines S, and S here can be replaced by C. Intuitively speaking, yes.
Okay.
But you need to have a formal argument to prove this, to show this.
Okay.
And
that
that
would
formal
be,
argument is?
that would be augmentation then?
Yes.
Okay.
But your intuition is right. All right, okay. Now, I used the whole lecture to basically review stuff. It's fine, because I think based on the way I got the response from you, I think many of you are still not clear about this concept. So this review session, I guess, is useful. We're going to have this session either now or later on. So it's fine. Now, decomposing into third normal form. Finally, let's move on to a new chapter. Okay. We said we know how to decompose a schema into a set of B, C, and F schema. At least that's lossless strong decomposition, which is recursively applying this rule here. And we said this guaranteed to give you lossless strong decomposition into B, C, and F. Not necessarily dependency preserving, but at least lossless strong decomposition. You follow me? What about, but I also told you decomposing into third normal form that's lossless strong and dependency preserving at the same time is possible. And what's the algorithm to do that? That's my question, right? The answer is, pay attention, okay? The answer is, you do exactly the same thing using this trick, using this algorithm. Meaning, whenever you find a functional dependency that has violated, of course now, the third normal form requirement, you decompose that into R minus Y and XY. And you keep recursively doing this, you will end up with, until you have no more functional dependency that has violated any third normal form requirement with regard to each of the smaller schemas, then you stop. And it guaranteed to give you lossless strong and dependency preserving decomposition into third normal form. You may wonder, like, why the same algorithm works now. For one thing, now the condition has been relaxed. That's rule number one. Second thing, which is critical, I'm gonna say that. You use this algorithm with one condition, which is you do not start with F. You do not start with F. You do not start with F. To run this algorithm. Rather, you start with, remember, we talked about two concepts. From F, you can derive F closure, which is all the functional dependencies that can be derived based on F. We also said the other thing, which is, do you folks still remember this F minus sign? The minimal set of functional dependencies. To give you an example, if I have if my input functional dependency is like this, what's my F minus? What's my F minus? In this case, it's just A determines B and B determines C. You don't need that A determines C because it's somewhat redundant. It can be derived based on other functional dependencies. So F minus is a set of minimal functional dependency that you can derive. But minimal set of functional dependency is more, is actually more more trickier than simply this. In that case, it's easy, just A determine B and B determine. What about, I'm going to change this. What's F minus? Can people tell me? What's F minus in this case? Obviously, I know whether it's obvious or not. What's F minus in this case? What's F minus in this case? Andrew?
Would still be A, B, and AC since
A determines B.
or yeah, A determines B and A determines C. Since A, B determines C can be found by augmentation.
So it's no longer A determines B and B determines C. You do need to keep A determines C in there. So minimal set of function dependency is tricky, actually. Because not only you can remove function dependency, you can also drop. You can drop attribute from the left-hand side as well, when needed. Intuitively speaking, A determines B, so that the B on the left-hand side here, the AB association means only A matters. B doesn't matter because A determines B. Once you have the same value of A, the value of B must be the same anyway. There's no point for you to associate B here. Intuitively speaking. Because from this, if you don't believe me, you can get AB determines BC by augmentation. And then you can break up the right-hand side, which gives you AB determines B and AB determines C. And this is a trivial function you can remove. Meaning from this, I can derive AB determines C. Which means AB determines C is unnecessary, it's redundant. So how do I formalize this argument? How do I go from F to F minus in any case? Well, this algorithm, unfortunately, is rather involved. I don't think I have time to go over that. So what I will do is I will post the slides on this algorithm, and you only need to read it if you're interested. I don't require you to understand how to derive from F to F minus in this class. I don't require you to know this. But you need to know there is this concept of F minus, minimum set of function dependencies. Does that make sense? And then that being said, how do you get lossless John decomposition and lossless John and dependency preserving decomposition into certain normal form? Well, start with F. Start with F. Step one, start with F and derive F minus. Then use the same decomposition algorithm before that I introduced to you for BC and F decomposition, which is if you have X determine Y regardless BC certain normal form requirement, decompose R into R minus Y and XY, then you're fine. Of course, condition is start with F minus. And this algorithm, we can prove that this algorithm guarantee you to have lossless John and dependency preserving decomposition into certain normal form. I guarantee you. You follow me? I have 1 or 2 minutes left. That's all I want to say for, that's all you need to know about normalization and function dependency. Finally, we're over this. Using, do I have a minute?
I do.
Every 1 minute is important. So, I'm going to give you a quick example where may overrun a minute. Okay? I'll give you one example where it is not in BCNF, and using the decomposition algorithm, you actually cannot decompose that schema into BCNF schemas and lossless John and dependency preserving into BCNF. That's the only example we haven't seen yet. We have seen the example where you can decompose it into lossless John and dependency preserving into BCNF, but we haven't seen an example where it is not possible to do it, right? So let me show you that using this example. I forgot the meaning of C, S, and D, right? C could be customer and supplier, Z could be a price. I don't know. For example, once you know the customer ID, you know the supplier ID, you know the price for the contract between them. That gives you CS determine D. You follow me? Yes? And I know, the other thing I know, each customer has a unique price, no matter which supplier you're talking about, which means some price determines the customer. Each customer has a unique price for all the contracts he or she signs. It means price determines, if you know the price, you know the customer. So Z determines C. So those are my functional dependencies. Is that okay? Now my question is this in BCNF? Quickly, can someone tell me? The first functional dependency is okay. Why? Because CS, the attribute closure is CSD. So this is the key. So the left hand has the key, so this is okay. You follow me? What about Z determines C? Is this in BCNF? It's not a trivial functional dependency, and the left hand side is not a key, so this has violated BCNF requirement. So this is no, not in BCNF. You follow me? Now we're going to decompose this using the decomposition algorithm we said earlier. How do I decompose this? Do you need to do anything for the first functional dependency? No, because it satisfies the BCNF requirement. The second one, yes, it violates BCNF requirement. So you decompose R into R minus Y. Y is what? C is this, and XY and XY is this is Z and C. R minus C in this case is what? So your R1 is this, and this is R2. You follow me? And this is guaranteed to be lossless Johnson combination. Why? If you do an intersection of them, you got Z, and Z determines C. So Z determines Z, Z determines R2. So the intersection determines one of them by the earlier theorem I told you. This is guaranteed to be lossless. But whether is this dependency preserving though? What's F1? And what's the F2?
Hey, Feifei, sorry, what's R1? The
S and D.
Oh, S. Oh, okay.
S what?
S and D. Because we use R minus Y. Y is C in this case. You got S and D. What is F1? What's the projection into this? In this case, is simply an empty set. None of the functional dependencies, the union of right hand side and left hand side, are covered by these two attributes. What about F2? Dependency, because the union of right hand side and left hand side is included by the attribute in R2. So R1 union F2, the closure of this equal to, meaning the union of the two is empty set and this, so all you have is Z determinacy. So let me be careful in this case. Z determinacy can derive this, yes. So the question really boils down to, can Z determinacy derive this? No matter how you do it, this time I'm pretty sure it doesn't give you that. So this is a lossless John decomposition, but not dependency preserving. So this example demonstrates to you that decomposing into BCNF, that's lossless John, and dependency preserving is not always possible. But if you check this with back to third normal form, things will be okay. You can do that. I see you on Wednesday, okay?